One of the most important questions for your robot to answer is, where am I? This is a deadwheel odometry pod, and it's a fundamental concept for FTC robotics, and it's the idea of localization. And by the end of the day, you'll understand some of the most common methods that you can use to be able to localize or figure out where your robot is inside of the field. I'm Coach Pratt, and I've been teaching robotics and design for over a decade now. And I've coached FTC teams to national championship wins. Today, I'm going to step you through the most common methods for localization of a robot to be able to answer that question, where are you, that are used inside the FTC. So in FTC robotics, the simplest way to figure out some localization is to simply use encoders on your wheels. So inside the back of all these motors, and typically under this cap here, is an encoder. And the encoder, most of them use Hall effect encoders at this point. And a Hall effect is effectively a little magnet. So you have a disc in the middle, it's got a magnet attached, and you have another sensor on the other side. And as that shaft rotates, you can keep track of just how many times this has spun. And typically, it's not just one full rotation. It's 28 clicks per rotation, or 50 clicks per rotation, or 40 clicks per rotation. CPR, you'll be able to find that on your motor data. But that's the simplest way. And then how can I actually apply that to a robot? Well, if I were to connect to that motor import on something like a tank drive chassis here, as I rotate these wheels, if I know the circumference of my wheel, and I know the encoder resolution here, I can figure out just how many centimeters I have driven forward using a little bit of math. And wheel encoders work great on something like a tank drive chassis. You're going to have not too much slip, you have a lot of high traction, and that really does make things a lot easier to simplify that. The problem with simply using a wheel encoder is that you're going to get a little bit of wheel slip. So sometimes what will happen is your robot will be sitting in place and it'll spin. And it will think that it has moved despite your drive wheels not actually moving. Like if you're running up against another robot, or you end up hitting something, or you hit something on a wall, and then it tries to push into that, it's still going to think it's moving forward despite it not actually moving forward. Wheel spin is particularly bad on holonomic drives like wheel spins here. So it's quite easy because mechanism drives are designed to slip. Using just wheel encoders on a mechanism drive is typically not going to be very accurate. You're going to have to use something that we'd like to call sensor fusion in robotics, which basically means you're going to put multiple sensors together to be able to get yourself some more accurate results. And on this one, you're going to use an IMU, or an inertial measurement unit, to be able to do a little bit of sensor fusion. So if you just have the wheel encoders on your motors as something like a holonomic mechanism drive, adding in an IMU, go build a pinpoint computer, has an IMU built in, and your control hub has an IMU built in. But what IMU does is it has a gyroscope and an accelerometer to be able to tell what point or what heading is my robot facing in. So you can start it up. If you say this is forward, as you rotate, you'll be able to know what direction it is that you're facing. So that is a great way of adding in a little bit more reliability to your system, but it doesn't really stop the problem of wheel slippage. To get around that, what teams in the FTC community have come up with is the concept of deadwheel odometry. And this is a deadwheel odometry pod. And effectively, what you do is you take a little wheel here and you attach this to an encoder. This is a rotary encoder. Again, it's Hall effect, and as it spins, you can keep track of just how many times it's rotated around. So as this wheel rotates, we can see that that sensor is rotating, keeping track of just how many ticks. This is the same thing that's in the back of our motors from earlier. And typically with dead wheels, you attach one on your y-axis and one on your x-axis to be able to keep track of x direction movement and y direction movement. So this would be called a two-pod or two odometry pod setup. So now instead of using encoders from your wheels, where you're going to have a lot more slippage, you can see that as I'm slipping here, my dead wheels would not be moving. But using some dead wheel encoder odometry, that can help us stop us from having that wheel slippage and worry too much about that. The problem with just using a two-wheel setup is that it doesn't tell you if you've rotated or not. So typically, that's where your IMU can come into play. So either using a Go Build Does pinpoint or using the IMU on your control hub, you can have one dead wheel to keep track of your X movement, one dead wheel to keep track of your Y movement, and then your IMU can help keep track of rotation. If you don't have access to a relatively accurate IMU, you can also have an additional odometry pod that you can slap on, and you can put on another X-axis here. so that now you can keep track of rotation just by looking at how far each individual ones are running. And then your Y still keeps track of your Y-axis movement. So you can have 3-wheel dead wheel odometry is another method for using odometry. Another last thing you typically see with odometry pods is you see them set up on springs. And the reason we set them up on springs is because those field tiles are a little bit squishy. And having a little bit of compliance to be able to make sure that these things are always forced onto the ground can really help, because sometimes you might find that you get run into something and your robot kicks off a bit. And of course, if you kick off, your dead wheel is no longer touching the floor. You're no longer going to have accurate measurements. Now, on top of mechanical designs for keeping track of where you are in space, there's also visual designs. And in FTC, we typically use something called AprilTags for that. And an AprilTag is kind of like a fancy QR code, or I guess it's technically a less fancy QR code, because you only have an 8x8 square, so you have a lot less data packed into one of these. So how an AprilTag works is you have known locations and known sizes for where AprilTags are around the field. And if you know what size the AprilTag is, and you know where exactly it is on the field, you can upload that pre-made map into your robot's processor. And then it can use some camera vision, like a Limelight 3A, a Husky lens, or a standard webcam, and it can calculate how big is that object inside of my camera's field of vision. And if I know how big it is, and I know what skew it is, I know how far away I am, and I know what angle I am in relative to this. And if I know how large that is inside my camera, and I know how big my camera is, I can calculate how far away I am. And then you can use that as another method of localization. And oftentimes what teams will do is they'll use those AprilTags, they'll use the dead wheel odometry, and then when a camera comes into vision of an AprilTag, they'll do a quick calculation, and they'll throw in, okay, I know exactly where I am on the field based on this AprilTag, and they'll update the errors that may have been occurring on top of those odometry pods for their localization method. So the most accurate robots using localization typically have 1, 2, or even 3 methods to use some sensor fusion, likely some dead wheel odometry, using some IMUs, and then also using a camera localization method to be able to take a look at those AprilTags and calculate where they are inside of space. The nice thing about AprilTags is they are absolute positioning as opposed to relative positioning. With dead wheel encoders, you can only really know where you are relative to where you started. You can know you've moved 20 paces forward. You can know you've moved 3 steps to the left relative to position point. But with an AprilTag, because you can upload a pre-made map of the FTC field, you can know exactly where you are on side of the field location. So it's a bit more complex to get set up, but it is also a bit more accurate and a bit more reliable when it comes up to figuring out where you are. If you're looking for more resources, you can consider joining the community down below. I'll have CAD and other code snippets you can take access to. If you're looking for more tutorials on how you actually do localization, you can take a look at my channel down below. I've got tutorials on using AprilTags with various different camera systems, and I'll have more tutorials coming up on using localization pathers, things like Roadrunner and Pedro pathing coming up in the future. If you got any questions, let me know in the comments. And as always, best of luck out there in this next robotics season.